Okay, in this chapter we're going to begin looking at firm-level decision making. And in simple economic models, we're going to assume that the goal of the firm is to maximize profits. And profits are the difference between total revenue minus total cost. And in this chapter, the first thing we're going to do is look at the cost structure of a typical firm. And then in the next chapter, we're going to also look at the revenue side of the market for a typical firm. So now we're going to look at a firm's cost structure. And in order to do that, we typically argue that firms are producing some good or service that they're going to sell. And what the firm does is combines certain inputs or factors of production in a certain way, presumably way that results in an efficient combination of inputs, and then given existing technology produces a certain amount of the product that they're producing. So when we look at this production relationship, we're going to look at different types of inputs that are being used to produce a given output. And here you're saying, well, okay, what is the production process? And it's some type of weaving. And what is our production relationship here? You know, basically we're producing these woven goods. So the quantity of woven goods we produce is our output. Then there's some production relationship where we're using physical capital in the form of this weaving machine, productive physical capital, and we're using materials, the types of wool that are in the yarn, and we're using labor in this case. So we're combining physical capital, materials, and labor, and we're producing this woven carpet. And in this production relationship, we typically assume that in a short-run decision problem, that some of the inputs are fixed inputs and cannot be varied over the period of time that we're considering the short run. So the same thing, we're producing an output. We have, typically capital is considered a fixed input. If you have a plant in a production process, in the short run, you may not be considering expanding the size of your plant. And typically, other inputs, such as labor, can typically be viewed as variable inputs. So when you want to produce more output in the short run, you can alter the number of people that you hire, but you're not changing the size of your physical plant. In the long run, it's a period of time that's long enough so that all of your inputs are variable. So over a period of time, you can decide that you want to expand your plant size. So that would be a long-run decision problem where you could vary the amount of any input. In the short run, it's only your variable inputs that can be changed, and other inputs such as the size of your plant or possibly land in some type of agricultural problem could be viewed as fixed inputs. And what we're going to show in this production relationship, output is Q. It's a function of the amount of capital that we're using. We're saying, okay, if capital is our fixed input, labor is our variable input, when we change the number of people that are employed, that's going to change the amount of output that we're producing. And our total product gives us the total amount of output that we produce given a certain level of our variable input usage. The marginal product, by definition, is the additional output that we produce given an additional unit of our variable input labor. So the marginal product of labor is equal to the additional output that we get divided by the additional amount of labor that we employ. And this gives us the marginal product of our input labor. And in most production processes, at some point, if you continue to add labor to a given size plant, or in this case, if you continue to add labor to a given amount of land, at some point the additional output that you get from a worker is going to start to decrease. So there's some point where the marginal product of labor typically is going to decrease in most production processes. And here we can look at a specific example. We're producing wheat. Here we go. We're producing wheat. Depends on the amount of land that we have, and land is considered a fixed input in this example, and any other physical capital that we're using would be considered fixed. And our variable input is the amount of labor that we employ. And this gives us our production relationship. It shows that when this is the amount of wheat that we can produce if we don't hire any workers. So if you don't hire any workers, you produce 0 wheat. If you hire 1 worker, you can produce 19 bushels of wheat. So what's the marginal product of labor? It's the change in output. Output goes from 0 to 19. It's the change in output associated with increasing your workers by 1 unit. So the marginal product of labor, it's the change in output divided by the change in your variable input labor. So here, the output goes up by 19 and the change in labor is 1, so you have 19 divided by 1. Okay, then when you add the second worker, output goes from 19 to 35, or excuse me, to 36, and the marginal product is 17. So you get 17 additional bushels of wheat when you hire a second worker. Hire the third worker, the marginal product of labor is 15, meaning you get 15 additional bushels of wheat. And then when you continue to hire workers, in this example, marginal product decreases, so that when you hire the 8th worker, you only get an additional 5 bushels of wheat. And you're assuming that the workers that you hire are equally skilled and equally motivated. So it's strictly you're adding additional workers to a given size field. And the amount of additional wheat that can be produced decreases because you're adding more of a variable input to a fixed size farm. And here, the marginal product of the second worker is equal to 17. The marginal product of the 7th worker is equal to 7. So you can see when you graph these points, if we graph the number of workers on the horizontal axis and the amount of wheat that's being produced, this is the total product of wheat. What you can see is as you add more workers, the total product curve, the slope of it tends to get flatter. And in this diagram, if this is output and this is the amount of labor that you employ, the change in output given the change in the amount of labor is actually the slope of this line. So the slope of this line actually gives you the marginal product of labor. And what you can see is as you hire more people, the marginal product of labor is decreasing. And here, the marginal product of labor is the additional output that you get when you hire one more unit of labor. And units of labor, it can be measured by the amount of time that the worker works. It could be an additional hour, it could be an additional week, or it could be a person that's employed for an additional year. So depending on the problem, the units can be different. But marginal product is the change in output given a particular change in the amount of labor that you're employing. In this diagram, the diagram A gives you the total product as you hire more workers. Graph B shows you the marginal product of hiring an additional worker. So here what they're showing is that how much additional output do you get when you hire more workers? And they've actually plotted this at the midpoint. So when you hire the first worker, the additional output that you get was 19. And when you hire the range between 2 and 3, the marginal product is 15. So what they've done here is they're plotting the marginal product of labor on the vertical axis and the amount of labor on the horizontal axis. So this is the marginal product of labor in our wheat example. And you can see as you hire more workers, the marginal product tends to go down. And here, if you added more land to this production problem, it would tend to shift the total product curve upward, which essentially means we have a new production relationship. And given that new production relationship, it affects the marginal productivity of each worker. And typically this happens. If you increase the amount of your fixed input, generally speaking, that's going to increase the marginal productivity of labor. And Sir Thomas Malthus is partly responsible for economics being called the dismal science. And you can see he was born in 1766, and Adam Smith wrote his book, The Wealth of Nations, in 1776. So you can see that Malthus was a contemporary of Adam Smith, but was somewhat younger. And what Malthus pointed out was that if you have a certain amount of land that's fixed and you continue to add workers to that plot of land, that you may be able to produce more output, but the marginal product of labor, the additional output that you produce for the next worker, is going to go down and down and down and down. So what his prediction was, in his day, a large percentage of the population was employed in agriculture. In England, it seemed that the amount of farmland was somewhat fixed, and if you continued to increase the population, what was going to happen is if the marginal product of labor continued to decrease, the additional worker would not be producing enough additional food to even feed himself or herself. So what Malthus was predicting is that based on this notion of diminishing marginal productivity of labor, that you'd reach a situation where the additional population wouldn't produce enough food to feed themselves. which is a very, very dire forecast. Malthus's prediction hasn't really come true because the world's population has been expanding, and the production of food has more than kept pace with the additional population. And what was the fallacy of Malthus's argument was, well, one, land wasn't completely fixed. You could expand the arable farmland. You know, sometimes you'd need to provide irrigation sources, sometimes you'd have to drain swamplands, but the land area itself can be expanded on. And even more importantly, what he didn't anticipate was the tremendous amount of technological change in agriculture. You know, for example, you have fertilizers and pesticides and herbicides and new types of seeds that provided a big boost in output for a given size farm. And analytically, you could flip back one slide and you could show that total product curve shifting upward, not necessarily because you were increasing the size of the farm, but because you were improving technology that allowed you to produce wheat on that particular farm. So it's been technological change that is something that Malthus didn't foresee. When we look at our cost structure, we can break total cost and say, well, total cost is equal to fixed cost plus variable cost. And our fixed cost is just our payment or the cost of our fixed input. And the fixed input stays the same and doesn't change based on how much output we're producing. Our variable cost is a payment to our variable inputs, and when we produce more output, we're going to incur a higher variable cost. Or another way of saying that is, any cost that you incur when you're not producing anything has to be a fixed cost. So in this picture, if we're producing cookies, we have physical capital, and presumably the physical capital in the short run is a fixed input. So our payment that's associated with our physical capital is our fixed cost. Our payment to our variable inputs, which would be labor in this case, and also the material costs involved in producing cookies, would be our variable costs. So one identity in our cost structure is total cost is equal to fixed cost plus variable cost. Okay, so now we're back to our wheat example, and you can see if we don't employ any workers, the quantity of labor is 0. We don't produce any wheat in this production relationship. Our variable cost is 0 because we're not going to be employing any variable inputs if we're not producing any wheat. And our fixed cost is $400. And this is a cost that goes to the payment. You know, in this case, if land is our fixed input, it's a payment to our fixed input. And you can see our fixed cost stays the same regardless of how much wheat we're producing, because it's a payment to a fixed input, and that amount of that input doesn't change in the short run. Okay, so now we go to, now we're employing one worker, and we're producing 19 bushels of wheat. You know, the marginal product of that worker was 19. Our fixed cost is still $400. Our variable cost is $200. And our total cost is fixed cost plus variable cost gives us a total cost of $600. Now we hire a second worker. Output goes from 19 to 36. Our variable cost, we're paying the second worker the same $200 that we did the first worker. So our variable cost is $400. Our fixed cost is $400. So our total cost is equal to $800. And in this diagram, we can go through, if we hire the 8th worker, output goes to 96. 8 times 200 gives us $1,600 in variable costs plus $400 in fixed costs is equal to $2,000 in total cost. So in this diagram, we're plotting output on the horizontal axis. This is the amount of wheat that we're producing, and total cost is on the vertical axis. So if we plot this relationship, if we're producing 19 bushels of wheat, our total cost is $600. If we're producing 96 bushels of wheat, we'd be out here. 96 bushels of wheat, and our total cost would be $2,000. So we can plot our total cost function, total cost on the vertical axis, output on the horizontal axis, and it would look like this. Okay, now what's useful for decision-making purposes is to break our cost structure down into, in this case, marginal cost. So marginal cost is the additional cost of producing one more unit of output. So if we take the change in total cost divided by the change in output, we're going to get the marginal cost of producing that last unit of output. Now the textbook changes to a second example, to Selena's Gourmet Salsa firm. And in this case, you can see what it starts with is it starts with not the production relationship, but it just gives us a total cost function. So if we don't produce any salsa, our total cost is $108. We know that if you're not producing anything, any cost that you incur has to be a fixed cost. So our fixed cost is $108, and that doesn't change regardless of how much salsa we're making. And in this case, our fixed cost plus our variable cost gave us a total cost of $108. Okay, now when we produce the first case of salsa, our fixed cost is still $108. Our variable cost is $12. So our total cost is $120. And now if we calculate marginal cost using the formula, marginal cost is the change in total cost divided by the change in output. So here total cost goes from 108 to 120. So total cost increases by $12. The change in output in this table, the change in output goes from 0 to 1. So basically the change in output, our marginal cost of the first case of salsa is $12. Okay, then the second case, total cost goes from 120 to 156. So our marginal cost is the change in total cost, 36, divided by the change in output, and output goes from 1 to 2. So marginal cost is $36 divided by 1, or 36. So if you have this total cost function that shows the relationship between output and total cost, then, and we know our fixed cost is equal to 108, or we just know that any cost we incur when we're producing no output has to be a fixed cost, we can take this total cost curve and calculate the marginal cost of producing an additional case of salsa. And we can see marginal cost starts out relatively low and then increases and increases and increases. And by the time you're producing the 10th case of salsa, your additional cost of producing just one case is $228. So in this case, you can see that as you produce more salsa, the marginal cost of producing a case increases dramatically. And we can graph this relationship. Here we can graph marginal cost. In graph B, we have marginal cost of producing an additional case of salsa on the vertical axis and quantity of salsa on our horizontal axis. So here, and typically we graph these at the midpoint. So when our output is between 0 and 1, our marginal cost is relatively low. When output is between 1 and 2, our marginal cost is equal to $36. And then here again it shows when you produce the 8th case of salsa between 7 and 8, our marginal cost is when our output is between 7 and 8, our marginal cost is $180. So you can have that table that shows marginal cost and output, and you can plot marginal cost. And you can see in this example, it's a linear relationship where marginal cost starts out low, and as you produce more salsa, increases. And why does the marginal cost curve, why does marginal cost increase as you produce more output? And if we think back into what the production relationship would look like when you're producing salsa, is why is it that marginal cost, or the cost of producing an additional case of salsa, increases? It's because, well, when you add another worker to producing salsa, output increases, but it doesn't increase by as much as from the previous worker. So what that means is as you produce more salsa, the marginal product of labor is going down and down and down. And if you have a relatively small factory and you add additional workers, you may get more salsa from an additional worker, but you're not going to get as much additional salsa as you did from the previous workers. So you're adding additional variable inputs, workers, to a given size plant with a given amount of machinery, and the marginal product is decreasing significantly. And you can see that when the marginal product of your input decreases in a one input problem, it means that marginal cost is going to be going up. It's also useful to break our cost structure into average cost. So average total cost is equal to total cost divided by how much output you're producing. Average fixed cost is equal to your fixed cost divided by how much output you're producing. And average variable cost is your variable cost divided by how much output you're producing. And now, using the identities in the previous slide, we can take the total cost function for Selena's salsa. The total cost function shows the minimum total cost of producing a given level of output. So when output is equal to one case, total cost is $120. When output is equal to two cases, total cost is $156. Okay, now we can use the identities in the previous slide to break our cost structure down into average total cost. So when total cost is 120 and we're producing 1 unit of output, average total cost is 120 divided by 1. Average fixed cost is our total fixed cost divided by Q. So in this example, 108 is the fixed cost. Divided by 1 gives you an average fixed cost of $108. Average variable cost, our total variable cost is $12 divided by 1 gives us an average variable cost of $12. Okay, then when output is equal to 2, our total cost is 156. 156 divided by 2, which is 78. Average fixed cost is 108 divided by 2, which is 54. Average variable cost is 48 divided by 2, which is 24. And using these identities, we could fill in the rest of this table. And what we see is, as output increases, average fixed cost goes down because we're taking a given fixed cost and spreading it out over additional production units. So our average fixed cost when output is equal to 10 is 108 divided by 10, which is equal to 10.8. So you can see average fixed cost is spread out over additional output and decreases. And if quantity increased beyond this, average fixed cost would continue to decrease, but at a diminishing rate. Average variable cost, on the other hand, starts out relatively low, $12, and as we produce more output, average variable cost increases. And the reason for this is because typically at some point there is diminishing marginal productivity of your inputs. So in order to produce an additional case of salsa, you're going to have to increase the amount of variable inputs you need in order to get your additional output. So when the marginal productivity of your variable inputs goes down, average variable cost increases. So now we can use the data in the previous table to graph average total cost. And we're graphing quantity on the horizontal axis, and we're graphing average total cost on the vertical axis. So when output is equal to 1, average total cost is equal to 120. And similarly, when output is equal to 2, average cost is approximately 78. When output is equal to 3, average cost is a little bit lower. Then beyond this level of output, when output is equal to 3, this is the output level that minimizes average total cost. It gives you the minimum point on your average total cost curve. Okay, then when you increase output beyond 3 units, you can see average cost tends to increase. And we're going to explain why average cost decreases at first, then reaches a minimum point, and then increases beyond that. Or another way to describe this type of an average total cost function is a U-shaped average total cost function. And here what we've done is we've actually graphed 3 relationships. We've graphed average total cost on the vertical axis, and we've graphed output on the horizontal axis, which we did before to get average total cost function. But in addition to that, we've graphed average variable cost on this graph. So we have average variable cost on the vertical axis. We have output on the horizontal axis. And what we get, if we plot the points from the previous table and fit a line through those, is we get average variable cost. Okay, then we can graph average fixed cost on the same graph. So on the vertical axis, we have average fixed cost. The horizontal axis is always quantity or output. So if we graph those points, we can see average fixed cost starts out relatively high at 108, and when we expand output, average fixed cost decreases and decreases and decreases, because we're spreading our fixed cost out over additional output. And if we increase output beyond this, average fixed cost would continue to go down. And as quantity approached infinity, average total cost would approach zero. But the rate at which average fixed cost is going down is much slower than initially. And we can also graph marginal cost. We can graph marginal cost as a function of output. And we get this, plot the points, fit a curve through it, and we get our marginal cost curve. So essentially what we've done is graphed 4 different types of cost curves on the same graph. And in the old days when you had overhead projectors, you could do it with individual slides, and then when you put one slide on top of another, you would get a graph that looked like this. And what you can see is our U-shaped average total cost curve is initially averages, then it reaches a minimum point, and then beyond 3 units of output, average total cost increases. And we can ask ourselves, well, why does average total cost decrease at first? Well, we know that average total cost is equal to average fixed cost plus average variable cost. So here we can see that fixed cost is going down, at a very fast rate when we're spreading our output, our fixed cost out over additional output. So average fixed cost is going down quickly here. Average variable cost is increasing, but it's increasing at a slower rate than fixed costs are decreasing. So initially you have average total cost, which is average fixed cost plus average variable cost decreasing. Okay, then at some point, average fixed cost continues to decrease, but at a slower rate. Average variable cost increases at the same rate, and at some point, the increasing average variable cost, essentially overtakes average fixed cost, so that the total cost, average total cost, starts to increase. And if you have a U-shaped average total cost curve, marginal cost intersects average total cost at its minimum point. So the point at which marginal cost intersects average total cost, here that's an output equal to 3, is the level of output where average total cost is minimized. And you can show that arithmetically, why the minimum point has to be where marginal cost intersects average total cost. Or intuitively, you can say, well, okay, if you calculated the average height of a person in an economics class, what you do is calculate the average height, and it might be 5'5". Okay, then if you bring in an additional student whose height is greater than average, if you bring in an additional student whose height is less than the average height of the class, if you bring someone into the class that's 5 feet, that's going to be bringing the average down. So here, if you bring in a student whose height is below the class average, it's going to bring the class average down. On the other hand, if you bring in a student who is taller than the class average, you bring in a student that's 6 feet tall, the class average, that's going to be bringing the class average up. So if marginal cost is above average total cost, it's going to be bringing average total cost up. If marginal cost is below average total cost, it's going to be bringing the average down. So intuitively, you can argue that the minimum point on your U-shaped average total cost curve is going to be where marginal cost intersects the average total cost. And explaining that, why the average total cost curve is U-shaped. Okay, initially you're spreading your fixed costs out over additional output. Average fixed cost is decreasing rapidly, but at the same time, if there are diminishing marginal productivity of your variable inputs, average variable cost is going to be increasing. So at first, average fixed cost goes down faster than average variable cost is increasing, so that average total cost decreases. And then at some point, average variable cost is going to be increasing faster than average fixed cost is going to be going down. And at that point, your average total cost curve starts to go upward as you expand output. And as we explained before, intuitively, if marginal cost is less than average total cost, then average total cost is going to be going down. But if you're at an output level where marginal cost is above average total cost is going to be going up. So here, where marginal cost is above average total cost, that's going to be pulling the average up. So the minimum point on your average total cost curve is going to be where marginal cost intersects average total cost from below. And this is going to be the output level that minimizes average total cost. Here you can argue that it's an empirical question what the shape of a firm's cost curves are going to be. And here the argument is it's more realistic in the sense that here you have marginal, here when you're increasing output, initially you have marginal cost decreasing when you're increasing output. And then beyond some output level, we'll say beyond Q0, marginal cost starts to increase. And if you ask yourself, well, what causes this? You know that your cost structure is derived from the production relationship that's involved. And in this particular production relationship, what's going on is initially you have increasing marginal productivity of your inputs. And that's why marginal cost decreases at first. But then beyond some point, you have diminishing marginal productivity of your inputs, and marginal cost starts to go up. So the reason that you have a marginal cost curve that's U-shaped is initially the production process has increasing marginal productivity. And then at the point where there's decreasing marginal utility, the marginal cost curve turns upward. Is this more realistic? Well, it's an empirical question. It depends on the production relationship that you're in. Okay, now we look at the difference between between short run versus long run economic costs. And in the long run, all of your inputs are variable. So there is no fixed input, because over time, if your planning horizon is long enough, you may decide to increase the size of your factory or increase the size of your farm in terms of land, if that was your fixed input. So the long run is a period of time that's long enough that all of your inputs are variable. And essentially what we've done here is looked at the cost structure for a firm. This average total cost 1 is the cost structure assuming that the fixed cost is $108, which is a relatively small fixed cost or a relatively small plant. Okay, this is the cost structure that we've looked at previously. Okay, now we're saying that this firm has, over time, if the time frame is long enough, can expand the size of their plant by investing in physical capital. And in this case, the fixed cost is $216. So what we have is another average total cost curve for our bigger plant size. And what you can see is if output is relatively low, your output is going to be less if you use the smaller plant, and it's going to be greater if you use the bigger plant, because your average fixed cost is much higher for the bigger plant. Okay, then if your output is beyond a certain point, say 7 units of output, your average is greater for the small plant than it is for the big plant, because you've been able to spread your fixed costs out over more output, and because you have a bigger plant, the productivity of your variable inputs is going to be higher. So in a sense, there is a trade-off between higher fixed costs involved in the bigger plant, but you have lower variable costs. And you can see in this example, if you have a plant size above 4, then it's going to be more efficient to use the bigger plant, or at least in terms of your average total cost, than it would be to use the smaller plant. So when we derive a long-run average total cost curve, essentially the long-run average total cost curve is going to be the envelope of those short-run average total cost curves that assume the optimal plant size. So if we look at a graph of this, we'll see. Now this is our cost structure for plant size 3. This is our cost structure if we have a bigger plant, plant size 6. This is our cost structure if we have a bigger plant, plant size 9. And what you can see what you can see from this graph is that our long-run average total cost curve is going to be the envelope of these short-run average total cost curves. And the size plant that you'd use then would be the size plant that's going to result in your minimum average total cost. So when your output, for example, gets above 3 units of output, which size plant should you be using? It should be average total cost curve 3. So you should have this particular plant size. Total cost gets above a certain level or gets near 6 units of output, your average total cost is going to be minimized by having a plant that's size 6. And then when you get near 9 units of output, your average total cost is going to be minimized using a plant that is represented by ATC 9, which is an even bigger plant. So your long-run average total cost curve essentially is going to be the envelope of short-run average total cost curves, assuming that you're using the plant size that gives you the minimum average total cost. And sometimes if average total cost is decreasing, over this range of output, we sometimes say that this production relationship exhibits increasing returns to scale because our average total cost curve, our long-run average total cost curve, is decreasing. So over this range of output, between zero and roughly 5 units of output, our average total cost curve is going down. Then roughly between 5 and 7 units of output, average total cost remains constant or is flat, which means our production relationship demonstrates constant returns to scale in production. And then beyond 7 units of output, our average total cost curve increasing returns to scale in production technically means that if you double the amount of each input in your production relationship, your output is going to more than double. Sometimes that's called economies of scale in production. And if you double your inputs, you're going to be doubling your cost, but your output is going to more than double. So what that implies is that your average cost of production is going to be decreasing when your production relationship demonstrates economies of scale. Similarly, decreasing returns to scale in a production relationship means you double each of your inputs and your output increases, but it doesn't double. It increases by a proportion that's less than doubling. So what that means is when you double your inputs, your costs double, but the amount of output you produce doesn't increase by a factor of 2. So what that means is your average cost of producing the product is going to be going up when you produce more output if there are decreasing returns to scale, otherwise known as diseconomies of scale. Constant returns to scale, you double each input, your costs double, and your amount of output doubles. So what this implies is that your average cost of producing the product is going to remain the same and be constant.